Hi, everyone. This is Kevin Limtow describing my design and implementation for Project 2. This is the system that is a combination of hardware and embedded software necessary to collect temperature readings and transmit them to an external device over a serial communication protocol like USB. Each measurement here is intended to be time-stamped to allow for plotting in an external tool like Microsoft Excel. And I'll have a graph to show you along with my video demonstration of the system in action, collecting temperature in a room temperature environment, being shifted into a refrigerator and vice versa. So I'll have some of that data to show at the end of the video. But just starting with requirements here, the stipulated requirements that we gathered from the course are pretty basic. We want to have a system that's going to be inclusive of several pieces of hardware and an embedded software application. The application is supposed to execute on Arduino, and it's going to periodically measure the value of a temperature sensor circuit. I tried to be disciplined about this, so my requirements in the design are actually supposed to be as implementation agnostic as possible. But at some point, I did need to get into the actual selection of the temperature sensor that I'm using for this project. As far as the requirements go, it's genericized as, hopefully working with any temperature sensor. The application is supposed to use a round robin with interrupts design. And as I get into the design and implementation of this project, I'll describe how I'm using interrupts to facilitate the workflow of this project. The intent is for the application to periodically transmit data across a serial bus to a host. So I've just decided to use USB for that because it was the easiest for me to easily connect my host PC to the Arduino setup that I have. In terms of some derived requirements here, I'm going to be interacting completely with the system using a serial monitor over USB. I'm going to be receiving temperature measurements and timestamps in seconds and temperature measurements in Fahrenheit. And they're going to be comma separated values so that I could just very easily copy and paste that into a program like Microsoft Excel. Then I could use a Sentinel character to break the round robin loop and end the program. Now, moving on to the design here, the hardware design of this project was a little bit more involved than the previous project, though not by very much. The temperature sensor I decided to use for this project was just a basic 10 kilo ohm NTC thermistor. I have some documentation that I point out associated with this thermistor, but I basically put it in a voltage divider circuit with the NTC thermistor in the R1 position for the voltage divider and the 10K resistor in the R2 position. And you can see in this setup here, the midway point or the junction between the two resistors of this voltage divider just goes into analog input pin A0. I have 5 volts going to it and the return path to ground. And so really basic configuration, I measure the change in resistance of this thermistor, and I can actually have that output translated to a temperature that I can then cast or convert into Fahrenheit and output through the serial monitor. So the nice thing about this thermistor is it came with a set of documentation, both the data sheet as well as an example code snippet. Thankfully, I actually didn't have to change that code snippet very much. I was very thankful for that. The code snippet takes in the analog input reading. And as we all know, the Arduino Uno, the ADC is, I believe it's a 10-bit ADC. And so we need to translate that. So that's this 1024 number in the code snippet that helps translate the counts of the ADC into an actual analog voltage reading. And then there is some math that is being conducted here that's specific to the thermistor I have in this configuration with the 10K resistor voltage divider. So it's really important that I was thankful that I had this code snippet, and the way I checked to make sure that this code snippet actually worked was I ran this program and I did a 2-point calibration once with the thermistor just dipped into ice water just to see that the temperature readings against this code snippet were coming out, in a reasonable fashion, close to 32 degrees Fahrenheit. And then I conducted the measurement of room temperature, compared that against just my home thermostat, and confirmed that we're within a couple degrees of expectation at both points. So I actually didn't adjust the code snippet at all, but that is one element of this design that I was reliant on. I guess software of unknown provenance, as it were. But I was able to calibrate and make sure that the temperature readings were in a reasonable state. The software design of this system is pretty straightforward, and maybe I'll just zoom in here so I can show this diagram a little bit more easily. There are two threads that are going on here. I guess, two streams that the system is expecting. One is for the user, i.e. me, to handle, and one is what the application is doing. There's quite a lot that I'm reliant on the user to handle. In my case, I'm going to be connecting the Arduino to my laptop, open up a serial monitor. That's going to help me start to observe the measurements coming on through the serial bus that I have. I'm going to be completely in charge of moving the system between the room environment and the fridge and back to the room environment in 5-minute intervals. That's totally on me. And it's also on me to input the Sentinel character to break the round robin loop and get the system into state of doing nothing. The application itself, the round robin loop, is pretty self-explanatory. Every 10-second period, that's mediated by just a 10-second wait time in the main loop of the Arduino code. Every time that loop runs, it's going to check for a Sentinel character first. Then it's going to go ahead, and if there was no Sentinel character, it's going to take a timestamp. It's going to convert that signal, whatever signal was measured, and I'll explain that in a little bit, to a temperature in Fahrenheit. And then it's going to go ahead and print the time and temperature out through the serial bus. If it does see a Sentinel character, it'll print an outro message and break the loop. What's key about this is an interrupt service routine. This is a timer interrupt that I have set up, which I'll describe in a little bit more detail. That's going to go ahead and read the analog input, A0 of the Arduino Uno, and store that input to the signal variable. So this is actually independent here. You'll see that the signal variable is written to in this ISR, and it's not converted to a temperature in Fahrenheit until it gets into the main loop. So my whole intent was to keep this ISR as streamlined and minimal as possible. So that's why it's only reading that analog input and storing it to a variable. You'll also notice the trade-off I made here, which is to take the timestamp in the main loop. So it's not perfect. The analog input reading will have a time offset from when the timestamp is actually taken. So those won't be at very precisely the same, but in the time scales of this project, which is in tens of minutes, I thought this was an okay trade-off to keep the ISR as streamlined as possible. And that's also why I keep the conversion math from the analog input reading to a temperature in Fahrenheit in the main loop as opposed to the ISR. So my whole intent here is to keep the ISR as short as possible. The other issue that I ran into as I was working on the implementation, so this is actually more implementation than design, but still the design is limited by the hardware I have. And of course, that is the Arduino Uno, has a 16 megahertz clock. The timer counter 1 register is only a 16-bit register, so it can only count up to values of 65,536. Even when I set that register to have a prescaler value of 1024, that means I'll have 15,625 counts every second of the 16 megahertz clock. And so, a 10-second interrupt, a timer interrupt, would require 156,000 plus counts. And that's not going to fit within the 16-bit register. So I had to get a little fancy, or I guess not fancy, but a little bit hacky about how I implemented this. So my decision here was to have the timer interrupt trigger every 31,250 counts. So actually much that's a little over 2 seconds. And what that does, or sorry, that is exactly 2 seconds. So every 2 seconds, the interrupt service routine actually activates, but I have a secondary counter, and that counter doesn't have the Arduino actually read the analog input until every 5th interrupt. So every 5th interrupt is 10 seconds. That's when the ISR actually goes ahead and reads the analog input. So that's a little hokey, but it was my way of getting around the design limitations that I have with the Arduino Uno, just because a 10-second period is pretty long in the scheme of the Arduino Uno. So in terms of the implementation, I have here some of my code. This was written in Visual Studio Code with the Platform IO extension. What you'll see here is I just start by instantiating some variables. You'll see that there's a sentinel character that I'm using, again, to break out of the round robin loop. I have my measurement period is a 10-second wait time. That's facilitated in my main loop. And I have the signal measurement as a volatile integer. The volatile keyword there just is really important to make sure it can be used outside of the ISR. I have a custom function here, which just converts that signal, the analog input signal, into a Fahrenheit temperature. This setup area is where I have to kind of go through that process of setting up my timer interrupt, and that's where it got a little bit complicated. I first start by disabling all interrupts, just in case. I think that's good practice. Disable interrupts when I'm configuring interrupts. So I just go ahead and do that with the CLI command. I am careful here to set the timer counter registers to 0 before I start configuring them, just to make sure I clear any settings that might be there from the previous set of code. I go ahead and per the data sheet of the ATmega 328P microcontroller, I'm going ahead and setting the clock select bits. That's these bits over here, CS10, 11, and 12. I'm setting in the values to 1, 0, and 1 to get this prescaler value to 1024. As I mentioned, I wanted to use the largest prescaler value as possible, so that way I didn't have to keep resetting that interrupt multiple times before I could take even one analog input measurement. So there's a lot of my reasoning there that I've described. I won't go through again. This is the value I was setting. So this count is associated with a 2-second interval. So every 2 seconds, the ISR will actually execute, but it's only on the 5th ISR that an analog input measurement will actually be taken. This is just a little intro message being sent to the user. Into the main loop, I'm checking for the sentinel character, as was seen in my software design diagram up above. And I am using the signal to F function to just change that or convert that signal value from the analog input to a Fahrenheit temperature. And then I'm printing that out to the serial monitor. And then here's my measurement period delay of 10 seconds. Here's the math that I was talking about earlier. Again, this was a code snippet that was actually given together with the thermistor that I purchased, which was quite nice. And I was able to verify independently that it was working as intended. And here is the interrupt service routine, again, where I don't actually read the analog input pin A0 until every 5th ISR. And that's, again, just due to limitations of the hardware that I have. So that's how my interrupt service routine is designed. And here are some readings that I gathered. But before I get into this, I'll go ahead and shift over to the next section of this video where I'll actually go through the measurements that I'm taking with the hardware setup. All right. All right, so this is the hardware setup with the Arduino Uno connected to a very basic thermistor circuit that you see here. This is the thermistor, that little black bead. This is just a 10K reference resistor there, or the V2 resistor in my thermistor voltage divider circuit. I'll go ahead and now start up my putty terminal, and that will open up a terminal here, which will gradually save a thermistor reading in degrees Fahrenheit along with a timestamp every 10 seconds. And I'll go ahead and let this run for 5 minutes to just let it equilibrate to the room temperature, though this entire circuit has been standing in my room temperature that you can see has been hovering around 73 degrees. So I don't expect that to change very much. But I'll go ahead and cut the video here and start again at the 5-minute mark. And so here we are, just nearing the 5-minute mark. The timestamp on the left is in seconds. And so I'm going to go ahead and shift my setup into a handy dandy space I have cleared out in the fridge here, being very careful to try to keep this entire circuit intact as I move it into the fridge. Alright. There we go. Nice and cold. Closing up the door, leaving a bit of space, and so just clocking it at 320 seconds, and we're already seeing the temperature drop down a bit to the temperature of the fridge. That is a thermistor, so the response time is fairly good, as we can tell. So I'll go ahead and stop the recording here. I'll let this run for another 5 minutes and reconvene around the 620-second mark. And so here we are once again, close to the 5-minute mark that I've had the system in the fridge. You can see that the temperature has actually started to stabilize here, pretty much around 32 degrees Fahrenheit. Might be the reason a lot of my produce is getting icy. So that's a knowledge point for me. Also just accuracy of the temperature sensor itself, which might not be perfect. I can certainly calibrate the system a little bit, knowing the resistance value of the reference resistor in my voltage divider circuit. But I'll go ahead and clock this at 650 seconds. Time from start of test. So now I'll let this equilibrate to room temperature for another 5 minutes here, and we'll go ahead and reconvene then. And here we are, just hitting the 5-minute mark post fridge time. So the system, as you can see it here, has been sitting out for another 5 minutes after I've pulled it out of the fridge. And you can see some of the temperatures are still steadily climbing a bit. These were the cold temperatures inside of the fridge, of course, somewhere sitting around 30, 32 degrees Fahrenheit, now settling in much closer to room temperature in the low 70s. So I'm going to go ahead and hit the Sentinel character that I've developed for this code, which should go ahead and pull me out of the loop at the 10-second mark. And there you go. I've entered the Sentinel character to end the program. And so now I can pull in this serial output that I've been collecting over time into my Excel spreadsheet. And now I'm sharing my screen once again. So I have the serial output of my hardware, or my system setup to collect temperature readings in ambient air and then inside of the fridge. I've gone ahead and saved all of this to a text file, which I'll go ahead now and open up with Microsoft Excel. I had a previous plot that you can see here. I'm going to go ahead and just pull this in, finish that, and now I have very basic plots I can generate. And you can see that here. So on the y-axis,
I have my temperature in degrees Fahrenheit, and on the x-axis here, I have time in seconds. And you can see that period or interval of time somewhere around the 5-minute mark. It took me, 10 seconds or so to get things in and out of the fridge. And you can see that temperature slowly drop and get, after a period of time, to the temperature of my fridge, which was hovering somewhere, in the low 30 degrees. Again, my calibration might not have been perfect. I don't have a very calibrated tools at the home. So I mostly just dipped my components in ice water to help understand where freezing was as a reference point. And then went ahead and pulled the system outside of the fridge. And you can see here, it took a little bit of a steady climb up to around room temperature, which is settling in at the low 70s. If I left this running for a little bit longer, it might have stabilized back out to the baseline temperatures that I was seeing early on. My hardware setup doesn't have a ton of thermal mass, but the components were still cool to the touch a little bit. The thermistor bead itself was probably not a big thermal mass at all, but could still contribute as to why we didn't hit very close to 73 degrees, which is where we're starting at the thermal baseline. But that's about it. So thank you so much for listening in, and I'll see you next time.